Welcome back, folks, to Precalculus. Today we're in Chapter 3, Section 5, talking about graphing rational functions, or in this case, fractional functions. Okay, so just a reminder that a rational function is of the form b of x equals p of x over d of x. Okay, a function over a function where p of x and d of x are polynomials and have no common factors. Meaning that you factored both of them, and if anything canceled out, then you did that. Okay. Recall that the domain of a rational function or a fraction is always all real numbers except any x where the denominator is equal to 0. So we can't divide by 0. Remember that. Okay, so looking at these first three examples to determine whether or not they're rational functions. First of all, you can ignore the b and g. Those are just an open parenthesis, closed parenthesis glitch in the printer. So it just means f of x is what you're seeing there. Okay, so anyways, determine if it's a rational function. Is it a polynomial over a polynomial? And in this case, no, because polynomials don't have variables underneath radicals. Okay. Over here, do we have a polynomial over a polynomial? Yep. Do we have a polynomial over a polynomial? Yep. So these two are rational functions, and we'll learn more about those today. Okay, so now let's talk about vertical asymptotes. Vertical asymptotes of a rational function occur where the bottom is equal to 0. Okay, the values that we're not allowed to have. So these are the excluded x values of the domain. Okay, so if we're doing a quick example here, we're saying 2 minus x equals 0. That would be a bad thing. So if I move my x over to the right, I get x equals 2. That vertical line right there is my vertical asymptote. Okay, if I go over here and I go to factor my denominator to x plus 5, x minus 2, now I use the zero product property. I get x equals negative 5 and x equals 2. This rational function has two vertical asymptotes. Okay, so now let's talk a little bit about how the graph behaves as we get closer to a vertical asymptote. So the y values of the graph are either going to approach infinity or negative infinity when a graph gets closer to a vertical asymptote. So you can see right here the function 1 over x. There's a vertical asymptote right here. So notice on the left side of it, our graph is approaching towards negative infinity. On the right side of it, our graph is approaching positive infinity. Okay. Also notice that the power of the exponent here is 1. Notice that they are going opposite directions around the vertical asymptote, okay? Almost as if they're quote-unquote crossing the x-axis, but they're not. You can never cross a vertical asymptote, but I just wanted to make a special note of that. If you take a look at the next one, I'm going to rewrite this. This is 2x over x plus 2 squared. We have a vertical asymptote here at negative 2. Now notice they're both approaching negative infinity here. Okay, you can plug in some values and see that. Okay, but notice the power is squared. The multiplicity is even. So it's going back the same direction it came from. Okay, so just a little fun fact for you to pay attention to. So now moving on to talk about horizontal asymptotes. Okay, so first things first, horizontal asymptotes, this is important. They describe the end behavior. So what is your graph doing at infinity or negative infinity of a function? They can be found by determining whether the numerator or denominator of the function grows the quickest. Okay, and we'll talk a little bit more about that here in a second. So to find the horizontal asymptotes, we're going to think of putting very large numbers into the function and seeing what happens. Okay, now before we do any examples, we're going to go down here to the table of how to find horizontal asymptotes. Okay, so think about this. You got a rational function v of x equals p of x over d of x. Okay, that way we don't have a little printer code error. So we look at the degree. So if the degree of p of x is less than the degree of d of x, meaning it is bottom heavy. Bottom heavy. Maybe we'll write that right here. Bottom heavy. Then the horizontal asymptote is automatically y equals 0. If the degree of p of x is equal to the degree of d of x, then there's a horizontal asymptote at the line where the leading coefficient of the numerator, so of p of x, divided by the leading coefficient of d of x, the denominator. So we'll put it over here. If they're equal, then the horizontal asymptote is automatically y equals a over b, let's say. Okay. Now, if the degree of the numerator is bigger than the degree of the denominator, meaning it is top heavy, there is no horizontal asymptote. Okay, so let's take a look at these examples now. So look at these examples, we're like, okay, well, the degree of the top is 0. The degree of the bottom is 1. So this is a bottom heavy. It's automatically y equals 0. Horizontal line, horizontal asymptote of y equals 0. We look at the next one. The degree of the top is 1 and the degree of the bottom is 1. So we take, to get our horizontal asymptote, we take the equation y equals and then leading coefficient of the top, 2, over the leading coefficient of the bottom, 1. So y equals 2. Lastly, let's look over here. We've got a degree of 1 on top and a degree of 2 on the bottom. So we've got ourselves another bottom-heavy rational function is automatically y equals 0. Okay, now it's your turn to determine what and if these graphs have horizontal asymptotes. So please pause your video and find the horizontal asymptote, if there is one, of each one of these functions. Okay, pause your video. Okay, so let's talk a little bit more about horizontal asymptotes. Now, where a graph can never cross a vertical asymptote, it can cross a horizontal asymptote. So to figure out if it does cross it, first we have to know what the horizontal asymptote is. So let's take a look at this example. Bottom heavy rational function. So the horizontal asymptote is automatically y equals 0. Now, if you want to know whether this function ever crosses this line, just set it equal. 1 over x plus 2 is equal. Find out if it's ever equal to your horizontal asymptote. Now, to solve this, we would just cross multiply little x plus 2, and we would get an equation 1 equals 0. So that is not true. So in this case, our function does not cross our horizontal asymptote. Okay, but if we take a look at this other one, this next one. So we got ourselves equal degree, second degree on top and second degree on bottom. So our horizontal asymptote is automatically 1 over 1, which is 1. So now we want to find out, does our function, which is x squared minus 1 over x squared plus 4x plus 4, does it ever equal 1? Okay, so let's find out. If it does equal 1 somewhere, we'll find out where. We'll solve for x. So what we're going to do is multiply both sides by x squared plus 4x plus 4. So those will cancel out. X squared plus 4x plus 4. We end up with x squared minus 1 equals x squared plus 4x plus 4. So we can maybe solve this now. Let's see what happens. So our x squareds are going to cancel out. we end up with negative 1 equals 4x plus 4. So we got negative 5 equals 4x, x equals negative 5/4. So what that means is when x equals negative 5/4, y equals 1. So our graph is going to cross at negative 5/4, 1. Pretty cool. We are crossing the horizontal asymptote in this case. Okay, so some tips for graphing rational functions here. Okay, so first things first, we want to find the y-intercept by evaluating f of 0, plugging in 0 for x. The next thing we want to do is find the zeros of the function by solving for x when p of x equals 0. Now notice I said p of x, like that's what we've been calling the numerator. Okay, our function is p of x over d of x. All right, remember that if the top is equal to 0, the whole thing is equal to 0. So that's going to give us our x-intercepts. We want to solve for our vertical asymptotes by solving for x when d of x equals 0. So our graph is going to be undefined when the bottom is equal to 0. Okay, and lastly, we're going to be finding horizontal asymptotes using the rules we just talked about, checking to see if it crosses, and then evaluating any other intervals if necessary to fill in the rest of the graph and kind of see the behavior. Okay, so what we're going to do here is we're going to do an example as a class. You guys at the end of class are actually going to do this one right here, and I'm going to do this one right here with you. Okay, so first things first, step 1, the y-intercept. Okay, the y-intercept. Well, before we do that, I should be being a good mathematician right now, and I should be factoring this to see if anything cancels. So this is actually going to be 2 times x squared minus 2. Okay, that's fine. And the bottom is going to factor into x plus 4, x minus 1. Nothing cancels. We're good to go, good to get started. Okay, so now y-intercept. Y-intercept, you can plug in 0 for x into either of these functions. It doesn't matter. I'm going to plug in the original one because 0 for x makes all the x's disappear. I get negative 4 over negative 4, which is 1. So 0, 1. Got ourselves a y-intercept. Okay, so now let's find our x-intercepts. Set your numerator equal to 0. Okay, I don't care about this 2. All right, I'm going to end up dividing it by it anyways because it doesn't have a variable in it. So I'm going to set x squared minus 2 equal to 0. So x equals plus or minus radical 2. Those are my x-intercepts, which is just a little bit bigger than radical 1. Okay, so right there, right there. Looking kind of funky right now. We'll see what happens. Okay. Next, we're going to find our vertical asymptotes by setting our denominators equal to 0. So I've got one at x equals negative 4 and another one at x equals 1. So let's go ahead and draw those, knowing that my graph is never going to cross a vertical asymptote. Okay, time to do the horizontal asymptote, which if we look at the original function, we see that we have equal degrees. So we better do leading coefficient over leading coefficient. Hopefully you're getting familiar with these rules. 2 over 1, which is 2. So y equals 2. Let's go ahead and draw our horizontal asymptote. All right, now our graph can potentially cross this, so we need to figure out, does it cross? Okay, then we're going to use some common sense to graph our function. So I'm going to set my original function, which is 2x squared minus 4 over x squared plus 3x minus 4 equal to my horizontal asymptote, which is 2. Okay, so let's do some algebra here. Let's solve. So I'm essentially going to multiply this thing over there. So the left side is still 2x squared minus 4. The right side becomes 2x squared plus 6x minus 8. Okay, good stuff. The 2x squareds are gonzo garbanzo. We got negative 4 equals 6x minus 8. I'll add my 8 over. We got 4 equals 6x. So x equals 4 over 6, which is 2/3. So we're going to cross at 2/3, 2. Okay, so 2/3, 2 is about right there. Another point. Okay, so now I automatically know what's happening inside here. Okay, I know I'm going to cross right here, and I'm never going to cross it again. So that means that my graph has to look like this in the middle, getting really close to that vertical asymptote and not touching it. Okay, on this side, I know that my graph is never going to cross this horizontal asymptote over here because I think I found where it crosses. It's not going to cross it again. So as I get closer to my vertical asymptote, I'm going to be going down. And as I get closer to my horizontal asymptote, I'm going to get really close. It's going to describe my end behavior, but I'm not going to cross it. Okay, now looking over here on the left third of the graph over here, I know my graph is not down here where my pen is because I would have found another x-intercept. So I don't even need to plot any more points. I know that the other part of my graph is up here. I'm going to approach the vertical asymptote and approach my horizontal asymptote just like so. So these do take a little bit of practice, and hopefully we get plenty of it. But right now I want you guys to stop the video, do this one on your own, follow all the steps that we did down here, okay? And I can help you guys in class if needed. But make sure that you complete this question 100% before you turn it in. Thank you, and I look forward to helping you.